beginning of your talk, the things about elliptic disks.
Yeah.
Normally, if, from the observational point of view, is there a possibility to distinguish them? For instance, if you get a full velocity, full radial velocity map, and compare it to the photometric properties, probably you will see some misalignment.
Yes, that's right. That's exactly what people have tried to do. They've developed, they've built full two-dimensional maps of the density in the inner disk, basically, and compared those with compare the major axes of the photometry and the kinematics to try to constrain precisely. There's very little evidence of triaxiality except when you have bars or when you have spirals. Things like that seem to be the main sources of triaxiality.
It is a crucial scenario if you were to produce worms, very interesting prospect. Except for the Briggs rules to confirm, do you have any other observation constraints that one can check? I have especially, I mean, I have two ideas right now. I mean, those are not forever lived, so
right.
at the end there must be some mixing of angular momentum transporting gas onto the disk or
right,
to the center, and there must be there could be a prediction about how much this is independent maybe of the geometry of the warp.
Well, right. Sorry.
Yeah. Second thing would be the large scale, or say the orientation of the warp with respect to large scale structure be an indication of such a mechanism taking place. I mean, especially thinking about these works of Bataillon around the 90s, where based on optical observations, they established a large-scale orientation of all the warps in a field. So is that something
well, I mean, in principal galaxies, to address your second question, sort of, but not really, they form along filaments, and so you might expect that there's some alignment between them, and then possibly something like that would give rise to alignment of warps. But yeah, I think that's going to be actually very hard to do. While in principle it sounds like a nice idea, I think it's very hard to constrain it directly through orientations, because after all, what really matters is what's happening in the last little bit when it starts hitting the halo, right? So, I mean, if I go back to this study, I mean, really you want to look at what's happening over there, what angle that gas is coming in, relatively speaking. So I don't think that's going to be an easy thing to do. Now, when we did the study, we also looked at what is happening to the gas in there, and one of the predictions we can make is about stellar populations, and we have looked at that. We don't have any observational constraints at this point. I mean, that has motivated a proposal, but we don't have anything to show about that yet. The thing I will stress, though, is that there is a lot of star formation going on there that is probably unrealistically large.
Also related to the warp accretion scenario, I wonder what role do the stellar disk play in these pictures? Should it also be warped, or you just ignore it?
Well, we don't ignore it. It's part of the entire system that's evolving. There are two main issues there, right? I mean, the main disk is certainly torquing the gas, and what it actually does, it causes gas and stars that have formed it to actually eventually settle into its own plane. Of course, it also tilts along as the system evolves. So there is some mutuality going on between, some mutual interaction going on.
But all these warps, I mean, stellar and gaseous warps should not coincide, of course.
No, they actually coincide quite closely. The main disk itself is fairly hot in the kinematic tomb recusants, so it remains very coherent, and probably unrealistically so in these simulations. But no, they should actually torque each other, and you would expect to see, I mean, this is why you see something here that's very flat. That's why you see that stars settle from one structure from the warp into the main plane.
The cold accretion, I think, the previous slide, I remember. So, I mean, that would pretty much be one of the main observational evidence, one of the first observational evidences for cold accretion, right?
Yeah, well, this is why we're excited about this result, right? Because we.
So is there anything special that makes it possible to see it in some galaxies and not in most of them? I mean, something that we have set up, or does that also get it?
Well, okay, I should say it's not just the cold accretion that gives rise to the warp. It's basically all the gas That is accretion. So really, it's not so much the cold accretion. It's directional, so that tells you that there is a directional flow of gas, which we tend to typically associate with cold accretion, but it's not purely cold accretion. There's also hot accretion. And the important thing here is that you're acquiring a single angular momentum vector. So it's really the fact that what the scenario tells you is that there is a hot dark matter halo with an angular momentum vector that's very different from that.
When you calculate these orbits in the triaxial halos, you do not consider any rotation of the system, right?
No, we don't. That was the slide I skipped at the very end.
So we have a bar, so that's the photon speed, and then the halo surrounds it.
So, okay, right. In the experiments with the orbits that I showed, the reason why I looked at the simulation in which the bar was destroyed was because I didn't want to precisely do what you just said, freeze a bar. So what I've done is, whenever I've calculated orbits, the potential I'm calculating is frozen. So there cannot be a bar in it. There can only be the disk inside it. And the triaxial halo itself is also not something.
You freeze the potential, but you do the calculations without assuming any system rotation.
That's right, that's right. And that is something we actually want to tackle, but it's a bit hard. But yeah, it is something. You're saying that the standard disk is aligned with the gases of or is
compare
which is aligned with the
nothing.
Okay,
I think the gas may be more aligned relatively. If you compare the angle between the stellar disk and the halos with the gas disk between the halos, these two angles, then the gas maybe more kind of mimic this. But this figure just show what, like you shown here, the middle is a disk and then you have the ramps here, right? So you have the angle. This basically gives the angle like yours. I don't know whether you think about this kind of value.
We don't have statistics. We have when you do this, we don't have the one.
Right, but how long you want?
Yeah. So I mean, I showed this. It was roughly at an inclination of 60, 50 something. I wouldn't say very much based upon one simulation. We did look at two simulators, in fact, because unfortunately what happened in the simulation that we started looking at late times, there's a merger, there's a satellite, and that kind of screwed things up for what we were interested in.